Hello and welcome to this video on the Yarkovsky and Yorp effects. It will be shown how these two combined effects can make the orbit of an asteroid change. In this slide, the location of the asteroid belt is shown. The belt is located between the orbits of Mars and Jupiter. Obviously, this image is not to scale and the two innermost planets are not shown. The asteroid belt contains bodies of different sizes. However, the Yarkovsky and Yorp effects will only impinge on the orbits of the smaller asteroids. For example, work on the asteroid Ryugu, that is spelt R-Y-U-G-U, showed that this body was affected by the Yarkovsky and Yorp effects. That body is just over 800 meters wide at its narrowest point, with a mass of 4 times 10 to the 11 kilograms. Now, Ryugu is not currently in the asteroid belt, and it is termed a near-Earth object. On this slide, there is a single asteroid. Sunlight enters from the right side. The sunlight is both scattered and absorbed. The scattered sunlight is not shown. The re-emitted absorbed light is shown as red lines. The absorbed light is re-emitted as thermal radiation. This radiation will have momentum and therefore exerts a force on the asteroid along with the scattered light. It is this that is called the Yarkovsky effect. Consider now an asteroid on the inner edge of the asteroid belt. The distance of this asteroid from the Sun will be about 2.25 astronomical units. At the Earth, there is a constant called the phi Earth. This is a measure of the amount of solar flux at the Earth. This flux can be used in a simple inverse square relationship to find out what the flux at the asteroid is for a particular period t. This gives the equation on the left. We can now consider Yorp. Well, to start with, what is Yorp? The thermal radiation emitted by the asteroid along with the scattered light induces a torque on the asteroid. This torque will change the angular momentum of the asteroid. In other words, it will change its spin. Also affected is the angle of the poles, and this may cause the asteroid to tumble. You have to bear in mind that these effects are very small, and for the case of Ryugu, the rotation period would change probably at the most in 1 second in 20 years. We can obtain an expression for the overall torque on the asteroid. We do this by splitting the asteroid surface up into small elements, and we consider the force on each of those small elements. Then, by integrating over the surface area of the asteroid, we can come out with the equation for torque, which is shown here on the right. On this final slide, we can see how the orbit of an asteroid will change. Now, this change will occur slowly over hundreds of thousands of years and even a few million years. Here, the orbit is shown as getting larger, but it's also possible that the orbit would reduce. Anyway, I hope you found this short video interesting, and thank you for watching.